Hello everyone, welcome to my channel. This is the second tutorial on the gradients editing on the fly. So essentially we are trying to edit the optimization procedure in deep learning models. And here you see I have annotated the figure here, so that's when you read the accompanying tutorial, you have better understanding of the background. So in this tutorial, we're going to cover the full training process as well as the techniques to edit the gradients. So first on the data. Now let me just run the first block first. So we have the basic packages loaded. And then here we're going to look at each component step by step. So first on the data side, we're going to download the MNIST data. So now this is something already built in the package itself. So we can just import the package from Torch Vision because we're using the image datasets. And then we're also using the transforms submodule, which is essentially to transform the image to a tensor object. Now, tensor is the object we use to represent the data and also to deal with the transformations, the training of the model used in the data set. So there are a few parameters we need to pass in. We're using the data sets to load the data sets. One is the root directory. So this is to tell the program where to store the data once we have downloaded. So typically, I would put in the data, or you can choose any other data sets you want. And notice that I'm using two function calls to load the data. One is for training, one is for test data set. Now, this is because there's a second parameter to say whether this is training or not. So, for example, if this one is for training, then this is going to be false. So it's basically used for test data sets. I also pass in the data as well in this case. And for the transform, so this is to say when we download the data sets, what kind of transformation do we need to apply, right? So I've loaded the toTensor function here or class here. I just call it in this case. So same for the test data set. One more parameter, which is the download. So do I need to download the training data set? And in this case, I choose yes. So basically I have downloaded a local copy of the training data set of MNIST. By the way, MNIST is the image data set about the digits classification, and it consists of 60,000 images for training. And I think it's around 10,000 images for testing. So just run this cell, and then you can see that it's downloading the images, which is very fast. Remember that to check your code structure outputs at a small scale, once you have run some operations, so it's also a good habit to double check. So now in this case, I print the training data sets, right? To say it's a MNIST data set and it has this many data points, and it has these different splits, and it's using standard transform, which is a default transformation. And I can also look at the different components embedded within the data sets, the training data objects. So I have data, I have target size, I have targets, which is the target label we want to predict. So if I look at the size, I can say that I have 60,000 images. Each of them is 28 by 28. So meaning it's a grayscale image, right? There's no channel, there's no color channel. And for the targets, also we have the 60,000 corresponding target labels we want to predict. It's also good to plot out just randomly or some image. In this case, I plot one image to see what it looks like. Right. So next, it comes to, so we have downloaded data sets. Now we need to build a loader such that it can help us to load the data set, the data once we need it for training purpose. Right. So there's this data loader class which can help us to do the job. So we also need to do it for training and test correspondingly. And in this case, these are sort of embedded in the loaders dictionary. So for example, I can use the training data loader for loading the training data sets, and similarly for the test data set. So this is the way I use the way how I use the data loader is to pass in the relevant data object, which I built earlier. So I have this data dataset object, which is to say I want to point to the trained dataset, and then with a specified batch size. Now the batch size meaning when I load datasets, how many images per batch do I load? Right. So in this case, I gave it 100. And do I want to shelve the datasets? And typically yes, because we want to add in some randomization in our operation, so that there's no systematic sort of bias in the operation. And similarly, we can give it the test data for the test dataset loader, and then also give it 100 and also shuffle the datasets. So this is where we have already built in the loader, and we can run it to say what it looks like. So now we can see that it's a dictionary of data sets, a dictionary or data type, and it has the two different elements. This is the location of the data loaders. Also, as we mentioned earlier, it's always good to have a double check on a small scale, right? So in this case, I look at the training parts of the loader, right? The training loader, and then what I want to do is to look at just one batch of data, image data, like what it looks like in terms of the shape, the size. So what we can do is to build an iterator first, right? So convert it to an iterator object, and then extract the first elements of the iterator. So what it means is that there's the iteration across different batch of data, and in this case, I'm extracting the first batch, and then print out the shape. So you can see that first batch is 100 images. Each image is the grayscale, one channel, and then this is the width, this is height, and also correspondingly we have this many labels. Right, so this is pretty much it for the data parts. And next we'll come to the model component. So in this case, the model is very component. It's very simple neural network. Right, so in this case, as I said earlier, when it comes to model, we have two parts: the parameters, which are often initiated in the init function, and also the architecture in terms of how this information, how these components, right, these weights interact with the input, right? So the input is X. So we're going to look at the first part. Now, I only have a simple two-layer neural network, and by two-layer, I mean two hidden layers. The first hidden layer, the second hidden layer. Of course, this is also our output layer. So actually, only one hidden layer, and then one output layer. So this is where we can pass in the parameters in terms of the size of the layer, which in this case, I'm using a simple linear layer, which is a fully connected neural network. So to make things simple, what I'm going to do is to just put a very simple 28 by 28 size for the input. And the reason is because that's our image is actually 28 by 28, and it does only one channel. So if it were 3 channels, like say if it's color image, then we'll multiply by 3 right, in this case. And also we're gonna do some projection, meaning we're gonna change the dimension of the data by some transformation. In this case, in the first hidden layer, I'm gonna transform it. I'm gonna put in 100 nodes. So that is gonna use this dimension to transform the input data. And then what's next is to use a second layer to hold this information and then put another transformation. So in this case, the input is going to be 100 because the output from the previous layer is 100 nodes, right? So I need to pass in correspondingly. And in the image datasets, there are 10 classes of images, right? Which is from 0 to 9. So I have no choice but to pass in 10, and this should correspond to the number of classes you have in the data set. Right. So this is basically the components, right? The weights or the parameters of the neural network, which are defined here. Next, what we're going to do is to transform the image data to a sort of a flattened fashion. So meaning when it comes in, is taking the shape of image like this, a square image. And then what we're going to do is because we don't care about the structure of the image, right? The geometric structure, we only want to use a flattened convolutional, the fully connected neural network, right? So meaning we're going to be using the linear layers. Then what we're going to do is to convert it to basically an array, a one-dimensional array, right? That's why for column-wise only sets to one column, and it has this many rows. So this is basically what we have in terms of treatment for data, and then we have we can pass in the first fully connected layer, and then apply right loop, and then the second layer, and then the right loop again. So basically right loop here puts in some nonlinear transformation so that we can learn something, right? In terms of the nonlinear patterns, and then we have the output. So this is basically a very simple neural network to make things simple. We can throw in, of course, convolutional layers to boost the performance of the neural network. After we define a neural network, we can print the model to see what it looks like. And of course, this is exactly what we designed. However, it is also important to look at the structure of the model so that we know in terms of how many parameters each layer and what is the shape of each layer. So there are a few utility functions here, which I think could be helpful once using the summary from the touch summary package. As you can see, after passing the size of the data, then it brings us the output shape of each layer, also along with the parameters, right? So the number of parameters in total. So this is one way to look at how many parameters we have in each layer, because we're going to look at one of the layer and change its gradients. Right? So this is how they can help us print the overall picture of the neural network. Another way is to use the print table. Right? So this is another utility function I have here. No need to go into details, but just to look at outputs. After running the codes, we have the first layer, which is the weights to interact with the inputs. We have this many parameters and also the BIOS. And note that the BIOS is automatically added per neuron. So each neuron has a BIOS. Now, because first hidden layer, we have 100 neurons, then we have 100 BIOSes. And that's another way to look at things. And next, we're going to build. So this is, again, another way to iterate different parameters of the model. So basically, we have a model built in earlier, and we can extract the parameters and then store all these parameters in a dictionary data format so that it's easier to work with these parameters. So in this case, I'm iterating through all the parameters, and then each parameter will have belong to the certain layer, and I'm extracting the name of the layer. So after running this operation, you can see that if I look at keys of the dictionary, I have basically the names of the different layers as we see here, right? And also, if I want to extract or focus on a specific layer or specific portion of the, for example, the BIOS portion of the output layer, then I can just announce what it looks like. So in this case, so this is the value of the weights of the parameters of the BIOS portion for the output layer, right? So, and also this is exactly what we're going to focus on later. So that's it for the model part, which is just to make things simple and intuitive to explain. The third portion, as we mentioned earlier, is cost. Right. So cost in this case is usually a scalar value, meaning just one single number, a metric. And so the question is, how do we turn a list of predictions to a single number? And this is what we want to do is through the coarse entropy loss and soft mass transformation, which I have some illustrated figures here. So intuitively, we have some predictions, which is unscaled, right? So this is raw prediction. 1, 2, 3 could be 100, could be 1,000. It doesn't matter. So each prediction is for a single image. So single image meaning for the class 1, class 2, class 3. This is my prediction. And what's happening is that we're going to use the softmax transformation, which is taking this form, to convert them to a list of probabilities. Now we can see that they naturally sum to 1, and we only need to focus on the elements with the highest probability. So this is our prediction, meaning our prediction is class 3. So this is easier to work with, right? If we convert it to a probability scale instead of the original scale. That's just for the scaling purpose. Now, next, we have this list of probabilities. What we can do is to use an equation, right? Use an equation to convert all these to a single number, which is called the coarse entropy loss, right? And this seems to be quite a lot, but we can read it from left to right. So first, we have the probability of each element, right, for each image. So I is the image I, and then K is the kth class. So and we have this many classes, we have this many images. This is just to sit over all the different elements. So for each probability outputs, we're going to apply a log transformation so that it's basically not exploding. Right? So if we convert to log, then it's always bounded. And then we're going to multiply by the true label, which is only taking the value of 1 or 0 if it belongs to class K, right? If it's 1, it's going to be 1. If it's not, it's going to be 0. So the general intuition, so instead of understanding how this works, it's good to go to understand how this metric will be, right, in different scenarios. So for example, if our target label is 1 and we're predicting the probability of belonging to 1 is 1, right? That means it's a good prediction, and the resulting cost, the CR, the cost entropy loss, will be low, and that matches our intuition. And similarly, if the true label is 0 and we're predicting is 0, then it's going to be low as well. On the other hand, if they don't match, right? If the prediction does not match, or is very far away from the true targets, then it's going to be very high. So in general, this metric itself it matches our intuition, and it seems a good cost to use in the model training procedure. Right, so we're gonna again verify and also show some codes to see how this can be calculated. And fortunately, the calculation is very simple because it's all handled by the function coarse entropy loss. So what it means is that we only need to pass in the prediction. For example, in this case, I have a 3-class prediction, meaning it has 3 classes, and I need to predict the value for each class. And I'm telling it that the true class is the first class, 0, because it starts with 0 indexing, right? So the first class is 0, and you can see that my prediction for the first class is the highest. Then naturally, it's going to be a good prediction, and I'm calculating the cost, which is 0.4, right? So this seems to be very low. However, if I predict to be the second class, which is not the first class, then it's a wrong prediction, and it should be high. If we run the codes, then it's very high, right? It's 5.0. So coarse entropy loss itself is actually quite widely used in training neural networks and especially in classification tasks. And lastly, we have the fourth component, which is the optimization. So optimization, usually we go with gradient descent. And to explain the gradient descent is actually very simple to understand. Like for example, in this case, this is our current value of the weight, and we're gonna minus off some portion. And this portion itself is sort of dominated by 2 components. One is the eta, which is the learning rate. It depends how big is the change. And the second part is the gradients of the cost with respect to the weight. So now this is, is gradients usually automatically calculated by the modern deep learning frameworks. However, what it covers is that first one is also, again, how big is the change? So gradient can be high, gradient can be low, but also the direction. So gradient can be positive, can be negative. Right? So in this case, if we are starting from this point and we're using gradient descent, and the slope itself is positive, right? So it's a positive slope, and eta itself, learning rate, is going to be a positive number. So we're gonna minus off positive number. So the W is going to be smaller. So we're gonna move into this direction. And this point, so this is the second point. So using this procedure, we are moving towards the minimum, and that's what we want. And the minimum is the minimum of the cost. All right, so this is a very simple case, but essentially we're using this procedure to let W itself go to the minimum, go to the optimal value, which is here. So remember, W is what we care about, and we are looking for the W that minimizes the cost. Okay, so that's a very simple intro to gradient descent, and also fortunately, using the gradient is very simple. We just call the SGD, which is a stochastic version of gradient descent, and pass the parameters, basically parameter 1 to iterate, and also the linear rates, which is in this case is 0.01. So usually we start from a small linear rate. So we have all these components already. Then we can just try to run one iteration to see what it looks like. And as I said, it's always good to start from small and instead of the full training loop. So I've put in some printers here. So first, I want to focus on the initial BIOS value, which is the BIOS outputs of the output layer, and I'm printing it as a NumPy object. So I'm extracting data and also coming to NumPy. Also, I'm printing out the gradients. So the way I can access gradient is just to access the parameters first and then get the gradients attributes. So I can access gradients. So this is before the training. And after I train for one iteration, I print out the values again to see how they are changed. So I can visually track they are indeed changing. Yeah, the model is indeed learning. Right. So basically, there are a few steps to complete one iteration of training. The first step is to get the prediction out, right? So we have some raw data, which is X, and we have a model. I'm gonna use the model to cook the inputs and get the outputs or get the predictions. And the prediction is per image level. So we're going to print. In this case, if X has 100 images, right? And our prediction is gonna be 100 image prediction for each 100 images. And this is actually for each class. So we have 10 classes, then in this case, I have 100 images, and each image has 10 classes. It's going to be a 100 by 10 matrix. And next, we're going to calculate the cost. So the cost is also can be simply calculated by calling the cost func we defined earlier. Okay. We're passing the prediction, passing the true label, and then we can get the cost. So before running the gradient descents, usually what we do is to clear the gradients by calling the optimizes zero grad function. So this is to say I want to clear the gradients. And the reason is because that's when we first initialize these BIOSes, the gradients may store in some value, some random value. We don't want to use that. We want to discard that and start from fresh. Right. So this is what it does. Lastly, after we zero the gradients, then we can start to calculate the true gradients for the current cost, which is here, right? The current cost. And what we can do is to say cost dot backwards. And this is essentially to say we want to use backward propagation to calculate the cost, the gradients of the cost with respect to the width, and then finally, with all the gradients calculated, we want to apply the gradients, which means to run the gradient descent algorithm. And that's simply optimizer dot step. So step means I want to execute the gradients so that the weights are changed. Right. So if we run this, naturally it's fast because it's one iteration and also 100 images, so a simple neural network. So you can see that this is the initial value of the BIOS, and that is initial gradients, which is null. And it makes sense because we don't have any gradients being used yet. And after one iteration, you can see that the weights are changed slightly, which is good because we don't want to change the weights too much just for the first iteration. And also we have the expected BIOS value here, the BIOS value here, and also the gradients of the BIOS. Okay, so that's for the simply one iteration. And we're going to show next is the gradient clipping and different ways to edit gradients. And